This meeting is being recorded.
Okay, so we're talking about depletion region, depletion width. So we know what is depletion region. It's important for PN junction. If you don't have the depletion region, you will not have a PN junction. So it's one of the basics that you have. So okay, let's say okay, now PN junction. So we have the P and the N over here. Let's say so now, so in the, I think in my video before, I didn't mention what's the doping concentration of each region of the P and N. So now, assuming if I don't say anything, we assume it's the same. P and N both with the same doping concentration. The difference is the one is donor, one is acceptor atoms. Okay, so we assume it's the same concentration. Now, so if it's the same concentration, let's say this is 110 times to the power of 22 per centimeter cube, and this is 1 times 10 to the power of 22 per centimeter cube, but it's a P and N. How does the depletion region looks like? So when I drew, it should be the same width. Sama ke ni? So if the same concentration, the depletion width area over here for P and N is the same. Okay. Now, what happens if I change the concentration? I make the N to power 23. What happens to the depletion region? Any guess? So 123, 122. I'll give you maybe 5 minutes to draw. So draw on your piece of paper, then send the drawing, draw the depletion region and send the drawing in the Telegram.
And there's more magnetic carrier, so the depletion region decreases.
Can you repeat that?
There's more doping concentration in N, so the region there decreases. The width of the region, depletion region decreases.
Why?
It decreases because it's easier for it to diffuse over to the P junction.
Okay. Let's listen to Liana. So Liana answer is opposite of your answer. Liana, why your answer like this?
First, because the N is more than the P, 10 to the power 23, rather than the P is 10 to the power 22. Because of that, the composition of the electron and holes is different between both regions. So that when
the depletion region is the lack of the free carrier.
Yes, this region is the lack of the free carrier. The whole move to the N and the electron to move to the P. They are more electrons diffused to the P, so that the region become narrow than the P.
More, can you repeat your last statement?
Because of the region of N is more than P, the total of electrons is more than P, then it can move freely to the P region and make a narrow depletion region at the P side, as at the N side, sorry.
Narrow depletion region in the P or the N? Here you draw in the P.
N part reduced because of the movement of electron more to the.
When you draw in your drawing, is like what I draw here or not? This is what you drew, right?
Yeah, different. Supposedly
Right.
the N
Let me see your
will become reduced. N type.
Banyak boleh drawing. Outdraw kan, outdraw yang drawing awak tu, awak draw N lagi besar pada P. So betul yang saya draw tadi.
Okay.
Dan tiba-tiba awak punya jawapan berbeza daripada apa awak draw. Ke macam mana?
N is more bigger than P. Then because of N, more electron move to the P when diffused. Then the N part region will reduce more than P region.
Macam tak tally lah apa awak cakap dengan apa awak draw, Liana. Ke saya salah faham? Orang lain faham ke?
Saya pun.
Mungkin saya yang salah faham ke? Alfian tak faham?
Tak.
Tak sangat.
N region more than P region. Then
what is more? Region more, carriers more, atoms more. What is more?
Region more because 110 to the power of 20.
What is more? Awak tak jawab soalan saya.
Region, so electron and holes become more.
Faham awak cakap, saya tak faham statement awak. Tak apa, kita dengar Alfian ni jawapan lain. Liana dengan Akmal sama lukisan yang saya tengok. Alfian, sama dua-dua region. Ke sana?
Is what I think because the depletion region is same because the recombination process achieve equilibrium. Yeah, but I think my answer is wrong. Maybe the answer is maybe like Haziq, I think.
Pula tukar macam Haziq. Kenapa macam Haziq?
Because we have more doping in donor atom, so maybe it diffuse more. Yeah.
Okay. Yeah, I will tell you the answer, everybody. The answer is what Haziq's answer is correct, but his explanation was, I don't understand. It doesn't make sense. His explanation. Liana's explanation is going towards correct, but her drawing is wrong. So saya jadi confused. So at least Liana's line of thinking is there. That you are trying to understand the thing. So now, okay, Depletion region is when electron and hole diffuse, right? So in the N region, you have majority electron. Here you have majority of holes. So this electron here will diffuse over here and the hole will diffuse to the other side. Okay, now for depletion region is also the other name. If you read textbook, the other name for depletion region is space charge region. Where a space is the same name, basically a space where you have charge. Okay, because the other part where there's no depletion region, there's no charge, it's neutral. Okay, so when an atom over here loses electron, it becomes, what's the charge? This side. If the atom loses electron, the electron goes over here. What's the charge over here?
Positive charge.
Positive charge. So it left with positive charge. 1, 2, 3, 4. Okay. So on this side, if the hole goes over here, it loses hole. So an atom that loses hole becomes negatively charged. The difference is on the concentration of the when the concentration are different, it means that katalah concentration different lah. Macam kalau nak if you want to visualize this for the same okay, for the same volume, let's say for this one, let's say hypothetically speaking, yang 10 kuasa 22 ni, 10 kuasa 22 ni, dia kata 10 kuasa 22 ni, 10 kuasa 23. So you will have maybe dalam satu besar ni, you have only like one atom. 10 kuasa 23 ni maybe 3 atom macam tu. For the same volume or area. Okay, tu maksud dia. So maksud dia ni basically per unit volume, the number of atoms are different. Okay, now so for space, in order for depletion region to occur, one electron have to recombine with one hole. So okay, so kalau kita hilang kat sini 1, 2, 3, 4, 5, katalah 5 electrons, it means kat sini pun kena ada 5 negatively charged ion lah. Dekat sebelah P pun kena ada 5. Tapi disebabkan dekat P tu the concentration are less, therefore the depletion region will be bigger. So 1, 2, 3, 4, 5. So the depletion region becomes like this. Okay. You understand? So the total number of charge equal side when it's thermal in equilibrium, like Afia was saying, it must be equal. Depletion region ni dia special region ni dia punya it has to be the same total number of charge on the P and the N. Dia kena sama. Kalau tidak dia tak boleh jadi, dia tak akan jadi depletion region, dia tak stable. So kalau macam ni dia stable, so like 5 over here positive charge and here 5 negative charge, but the depletion width at the N is much smaller than depletion width at the P. Okay, you have any question on this? Hello?
No.
You understand?
But the region itself different size or same size?
Ni different lah. Here is like this, the depletion width.
That one the depletion region, but the total of size P and N can draw same size like?
Tak faham macam mana? Size apa?
Yang size P dengan dengan N ni, walaupun dia different 1.10 to power 23 dengan 22, kita lukis dalam bentuk yang sama ke nak different?
You mean this size?
Yes.
It's normal. It depends. It's a good question. It depends on the design of the device. So kalau kita design dia sama, so macam ni saya design ni lebih kurang sama lah, P dengan N. So then dia samalah. Cuma dia apa? Total macam nak cerita, dia total tu sama tapi macam ni lah. Yang ni size dia sama tapi dalam tu beza. So maknanya kita boleh make it we can design it to be the same, we can design it to be different, but the concentration there dependent on the doping.
Oh, okay, I understand.
Madam,
Yeah.
kan number of charge ni kan sama kan dua-dua kan? So apa yang membuatkan depletion region tu tak sama?
Ni?
Oh, internal tu.
Okay. Any more question?
No.
Okay, just to test your understanding, I will give another one. Okay, here P plus N plus. Okay, biasanya kalau kita tulis macam ni P plus, maknanya the more plus you have, the higher the doping concentration. Okay, kalau saya tulis P, N, kalau katalah saya tak cerita kat bawah ni berapa I don't tell you what are the doping concentration. I just put it in terms of this. You should know relatively doping, ni higher doping than this. And this is maybe the same doping or this roughly. Tapi kadang-kadang dalam soalan, saya akan beritahu, okay, ni the N plus is here, N plus is 10 kuasa, let's say 23 per centimeter cube. Yang ni 10 kuasa 20 per centimeter cube. Yang ni 10 kuasa 23 per centimeter cube. Okay, draw me the depletion region at, let's say, at minus 40 volt. Okay, so saya give you 5 minutes. Stop recording. Macam mana?
There are less free carriers at depletion region.
Yalah, kenapa? Why? Why magic happens like that?
Yeah.
So remember, when you apply a negative voltage, it means that at the end you apply a positive, at the P you apply negative, right? Yes? Yes or no?
Yes.
So the free carriers over here, the electrons over here, their majority at the end is electron, the majority at the P is hole. So the electron here, the electron here will want to go to the positive side, and the hole will go to the negative side. So if you can imagine, it goes this way, the carrier. So that's why in the middle, the depletion region getting bigger, because the free carrier are getting away from the junction. Yang elektron ni pergi kat sini, hole pergi kat sini, so semakin besar. Okay? Right, so okay, the reason why I asked you to draw minus 100, minus 40, apa nama ni, Alfian saya suruh buat minus 20, because the initial your answer, right? Both your answer, Alfian dengan kalau saya kata masa minus 40 tu kan, both your answers are correct. So it depends on how, because you don't have a appreciation of minus 40 ni besar ke kecil. Minus 40 sebenarnya besar. So to be strictly correct, Alfian's answer is correct. So by minus 40 tu dah patut go, dia dah deplete. Yeah, so Alfian's answer dia deplete yang ni, and then dia deplete the whole of the P, and then it goes slightly to the P++. Okay, so but assuming that you don't know the writing difference, what Haziq and the rest, Liana and Akmal answered was also correct. So it means that the P+ should have bigger depletion region compared to the N++. Okay, so but as you make the voltage higher, if you make the reverse voltage, bukan forward lah. If you make the reverse voltage higher, the depletion region should be bigger. So kalau Alfian tu patut draw ke sini sikit, and maybe but overall yang this side should be smaller than this side. Sebab the voltage, negative voltage kat sini dia cover kat sini saja. Yang ni dia cover yang ni plus yang ni. So that's why at the P++, the depletion region ni must be smaller than the N++ side. Okay. Faham ah? Faham ke? Ada soalan ke? Okay.
Prof, kiranya P++ get depletion region because of the attraction between P+ and N++.
Dia semua, dia kira satu ni. Dia kira macam ni, satu ni P, satu ni N. So dia the way kita look at it, dia PN kan, ni kira macam satu, dan kali lain lah. So ni satu P, and satu ni satu N, ni satu ni P. Cuma P ni dia akan pergi, bila deplete, dia akan deplete PN macam tu, dia akan deplete away from the junction. Tapi bila dah habis, it will start to deplete first the P and the P dengan N yang dekat junction tu. Tapi bila all the P+ having all depleted and ada voltage lagi, dia akan pergi ke P++ macam tu. So dia akan pergi macam ni. Tapi bergantung. Ni baru 3 region. Saya boleh buat soalan 10 region. Kau nak menggila lah. Go crazy for the final exam. I will draw like multiple regions. So, kecil besar. And this is not unusual. Kalau design yang betul-betul pun dia boleh macam tu lah. Kita boleh tukar doping at certain region. There are certain reason why we do that. Ada macam-macam reason lah kenapa kita nak macam tu, kita nak increase efficiency dia. So the depletion width will also change with the doping concentration. Okay. So kalau dah saya kata sini I, nanti bila buat buat untuk your assignment lah, sekarang ni kita belajar PN lah. Nanti you will find PIN. Allah, tak nampak pula. Your internet connection is unstable. Ya. Apa ni? Awak nampak separuh. Okay, stop sharing ya. Bahaya internet mahal, lepas tu unstable pula. Tengok tu, dia slow. Dia tak tally, tak sama tu. Nak kena dia dah lag. Nampak? Dia lag lah. Tak nampak saya tu. Stop sharing. So ni tak pernah jadi macam tu. Awak semua pakai Unify ke?
Yes.
Yes.
Ayo, lagging lah. Lagging. We cannot show how. Mana nak buat? Mana nak buat ni? Dah Ajar pun nak probably dulu. Nampak saya punya drawing ni. Ya, kena nampak balik. Yalah, tapi awak nampak PIN saya ni kan. So dekat I, nak okey dia dah okey dah. So I ni the I is, kalau kita dapat awak biasa P dengan N, kat I ni apa? I ni intrinsic region. Okay, so I can make a device PIN, and PIN siapa yang dapat photo detector tu, PIN photo detector is more is a better compared to PN junction detector. Kenapa? Then you have to find out why. So kita nak buat, kita akan buat design PIN, and when we say I intrinsic, in real life intrinsic is not zero doping. Dalam live tu bila kita buat in practical, when we go to the factory apa semua tu, I ni dia takkan jadi zero doping, dia makin jadi 10 kuasa 15. 10 kuasa 15 tu sikit lah. Ni macam due to impurities, kat situ dia 10 kuasa 15. Ni biasa 10 kuasa 23, 10 kuasa 22 ke 10 23 ke. So you need to be able to draw the depletion region for this as well, for different voltages. Okay, ataupun saya boleh buat 4 region. Saya buat P++. Tapi hak ni saya buat N+. Pun boleh. As long as you understand the concept, different question I give you, awak boleh jawab jugalah. Okay, any question on this before we go? Next, we need to go to the quantum dot quantum. Well, any question? Tak ada. Ada?
Madam.
Ya. Yes.
Maksudnya kalau reverse bias tu, depletion region akan increase at both side, N dengan P.
Yes.
Itu.
When you apply negative voltage, electric field will be need to be applied to both side. Dia tak boleh pergi one side. So maknanya katalah kalau banyak ni, mana minus 40 tu dia akan the electric field will be equal on both side, dan depletion region different. So macam electric field is just voltage per over distance, right? So the voltage will need to be distributed in the two side, the P and N. So electric field is voltage over distance. So since the distance different, okay, the 40 volt will be applied at both sides. Tapi dia punya electric field will be different because of the distance. Bila kita kata electric field, E equals to V over D kan, yang kita belajar dulu. E equals V over D. This V is the voltage that you apply, your negative voltage ke positive voltage ke. D here, distance apa? Depletion distance. So the electric field in the PN junction will not be the same if we change the doping concentration inside the semiconductor, because the electric field depends on the width, how much voltage is distributed along the width, and the width of the D ni, the width of the depletion region ni depends on the doping concentration. Okay, so menjawab soalan, dengar ke saya? Dia tak stable pula. Can you hear me? Hello?
Boleh. Lagi sikit.
Aduh. Manakah? Mula lagi ni. Ni pun lagi. Okay. Okay, dari lagi ni pula. Kita stop sharing. Tapi menjawab soalan Alfian tu, maksudnya the voltage will be applied at both P and N. So kalau therefore the depletion region should increase at both sides, but the rate at which it increases depending on the doping concentration of either side. Okay. Ada soalan lain? Tidak ada. Dia lagging lagi. Tak nampak. Kalau saya scroll pun tak nampak. Dia lag. Beginilah. Harapnya kita akan start sekelas. Physical soon. Sibuk undi kita ni. Dapat Prime Minister pun tak dapat lagi. Tak boleh lah. Dia lag. Sebenarnya saya nak kena complain ke apa ini file ni. Lama dah saya tak buat kelas online ni dulu. Okay. Alright. Seems okay now. So now quantum well and quantum dot. Okay. So the one that everything that I taught you since the beginning of the class until now, we call that is bulk semiconductor. So bulk semiconductor means that dia besar lah, is big. Okay. Now, what happens if we make the layer thinner? Remember, I told you before in the class that when we grow our semiconductor, we do epitaxial layer and layer macam kuih lapis, layer by layer by layer. So if the layer, or if each layer here is like 1 micron or more, bigger than 1 micrometer, this is called bulk. Dia doa dia tak tally lah dengan apa saya cakap. Suara saya pun slow juga ke macam mana? Lagi juga suara saya ke macam mana? Hello? Kenapa tak ada suara daripada awak ni?
Lagi dah.
Allah, macam manakah? Apalah, saya ajar sikit sini, nanti awak baca sendirilah. Awak pergi tengok banyak, or you can go and read about quantum dot and quantum well. Okay, why before we talk about quantum dot and quantum well, why we have quantum dot and quantum well? Can you hear me smoothly or lagging?
Yes, okay.
Kan, now.
So kalau lagi we tahu. Kalau saya cakap laju tak dapat my point. So the reason why we do quantum well or quantum dot ni because it increases the efficiency of our devices. Bila dia ada the physics changes. Okay, bila kita make it very small, macam nano, kata nano dot, nano apa semua tu, when it becomes nano meter, very small, the physics change. So and then when the physics change, we can manipulate the physics such that it improves our devices. So biasanya LED nowadays, if you go and buy LEDs in the market, most of the LEDs are quantum well LEDs. Okay, quantum well LEDs. So what does it mean? Okay, bulk semiconductor, is big, like 1 micron or more, it becomes bulk semiconductor. Now, if you try to make the epitaxial layer thinner, so instead of macam saya draw ni, dia buat kecil je macam ni, layer macam ni. So you make the epitaxial thinner. So kalau quantum well, the thickness of this the thickness of this quantum well layer, it will be roughly like here. So, tengah saya ke? Senyap je awak dengar kata kau lagging beritahu.
Tadi like
Aduh. Tapi lah lebih kurang je lah. So baca nanti quantum well ni basically FT dia thin, roughly like more than 100 nanometer. Okay, but less than micron. That's quantum well. But if you make it thinner, the epitaxial thinner, the layer thinner, what happens is you will get, kalau ni top view ni top view. Kalau buat this is quantum well, bila quantum well tu layer tu macam apa nama ni, macam kuih lapis lagi. Tapi kalau kita go for like 10 nanometer or less, dia jadi quantum dot. So what happens is if it's the layer is too thin, because of the stress and the strain inside the semiconductor, dia akan jadi macam ni. Kalau top view tu akan dapat macam jerawat. Awak boleh Google lah gambar dia. Kalau ni top view, kalau side view, side view akan nampak macam side view, saya nak draw. Side view awak akan nampak dia macam ni. Macam itu. Dia macam islands. We call it quantum dot islands. Dia jadi macam biji-biji macam jerawat. Macam itulah. And random. Dia akan besar kecil. Tapi we try to make sure that each of the island ni lebih kurang sama. And this island is called quantum dot. And the physics of the quantum well, quantum dot, dia dipanggil quantum confinement. So basically what happens is dalam quantum well, the carrier, kalau bulk kan, kalau bulk, saya draw bulk ni 3D. Kalau bulk, the electrons can travel anywhere, semua arah. Okay, bulk, the electron can travel like go here, go anywhere inside the semiconductor. But if it's a quantum well, the electron or a hole can only travel dekat dekat layer tu. Macam satu arah je. Tapi 2D. Kalau bulk tu dia 3D X, Y, Z. Ni macam XY je macam tu. Dia boleh travel kat sini je. So kita confine the carrier. Carrier tu kita tetapkan duduk kat situ. Dia tak boleh merayau. Kalau carrier tu merayau, kita nak control dia tak boleh, susah sikit dia sebab dia ikut suka dia nak duduk kat mana. Tapi kalau kita boleh design dia such that the carrier duduk pada satu tempat, it will make the device more efficient. Kalau kita pandai when we design the LED or biasa quantum well ni LED lah. Solar cell ada juga quantum well. Apa nama ni, laser of course, quantum well, quantum dot ada. So okay ni. Kalau quantum dot ni, so yang merah ni quantum well lah. Ni hitam quantum bulk, merah quantum well. Kalau quantum dot ni dia jadi besar ni je. Cepat nak draw. No, nampak? So this is quantum well. This is bulk. And this is ini kecil ni quantum dot. So quantum dot tu dia macam, it's like we confine electron tu. Sebelum ni electron tu, yang ni dia boleh pula elektron ni boleh jalan semua arah. Yang ni elektron boleh jalan arah ni dengan arah ni. Quantum dot ni, kalau kita berjaya membuat quantum dot, elektron tu dia duduk kat dalam tu je. Dia tak bergerak. Kita confine the carrier and it cannot move. Kita nak elektron duduk kat situ, duduk kat situ lah. Macam tu. So basically we can control where the carriers are. So elektron tu duduk kat sini. So ni when I draw it structurally. So you need to be able to draw the energy band diagram. Of the quantum well and quantum dot. How? So katalah ni bulk lah. Ni energy band diagram of the bulk. You see EV. Let's say this is gallium arsenide 1.4 EV. Okay. Ni bulk. Kalau okay. In order for us to make quantum well or quantum dot, dia syarat dia kena sandwich between two different band gap, two different material with different band gap. Dia kena sandwich. So maknanya kalau saya draw tu dia kena macam ni. Dia kena, kalau saya draw structurally dia kena ada, biasanya orang tak draw macam ni, biasanya orang draw macam ni. So macam ni. Kalau awak tengok LED, awak buat assignment awak nanti kan, awak akan macam dapat macam ni. Ni macam, ni kuih lapis tadi kan. So dalam kuih lapis tu macam ni lah. Kalau lah merah ni nak jadi, merah ni nak jadi apa nama ni, quantum well region. Dia kena sandwich dengan dua different region atas ni, bawah ni. So for example so kalau merah ni gallium arsenide, dia kena kita kena sandwich dia between different material yang with a higher band gap. Gitu. Nampak tak? So yang biru ni with a material with a bigger band gap. So maknanya kalau merah ni quantum well ni gallium arsenide 1.4 EV, yang sandwich dia tu, roti dia tu, alamak, kenapa ni hilang pula? Banyak cubaan. Okay. Tak boleh. Okay. So yang apa, the sandwich material ni have to be bigger than gallium arsenide. So gallium arsenide ni the quantum well material. So the apa nama ni, the sandwich material should be something bigger, maybe aluminium gallium arsenide, maybe we say 1.6 EV. Okay, so syarat dia kena always sandwich. So kalau quantum dot pun dia kena sandwich between dua material. So kalau quantum dot material ni gallium arsenide quantum dot, surrounding dia ni semua kena material with bigger band gap. Can be gas juga. So you need to know the band gap. So kalau kita draw structurally, this macam yang tadi ni saya draw 3D, 2D macam ni. So you can have this quantum well over here, then you have the material of your other material over here. So it can be gallium arsenide here, then aluminium. Gas over here, this gas. Okay, so ni structurally. So kalau kita nak translate this to energy band diagram, so if you want to translate this to energy band diagram, it will be, ni material, saya tak draw lagi. So I will only draw in terms of material. I would need to be able to terjemahkan benda ni into PN junction. PN junction is a device. Yang ni semua baru material. Kita tak buat device lagi. The simplest device is the PNN. Yang ni mungkin semua ni we can draw. Ni semua intrinsic pun boleh. Just material. Okay, saya tak draw, tak ni. Kalau nak buat device, tak kena tambah P kat sini, kena tambah N kat sini. Okay, so ke mana tadi? So kalau saya draw ni in terms of energy band diagram, it will be like, okay, so dia macam ni. Wah. Jadi, so kita draw tadi, saya ambil color yang sama, saya ambil ini. Kita draw sebelah-sebelah. Yes. So kalau saya draw energy band diagram of this, so atas ni color biru kan, yang ni biru ni, sandwich dia tu saya akan draw pun dia color biru energy band diagram. Okay, so start with the higher, the bigger band gap. Okay, sandwich dia kiri kanan dia bigger band gap, same band gap ni, let's say 1.6 EV. 1.6 EV, production band, production band. So in the middle here is the quantum well. So quantum well ni yang ni, yang merah. So it has a band gap lower, smaller than the band gap of the sandwich material. So kita buat macam ni. Dia 1.4 je kan, tak jauh sangat beza. Okay, 1.4, so macam ni. 1.4 EV, PC EV. So macam mana kita draw, kita akan just sambungkan dia. Macam tu. Okay. So the energy band diagram of the quantum well material macam ni. So kalau tengok macam ni, saya tahu it's a quantum well, but biasanya kita akan draw ni tak besar. Biasanya ni saya exaggerate sikit, besar sikit lah. Biasa kita draw smaller. As long as this region is smaller than the other two region. So quantum well tu kena small. Kalau quantum dot, dia jadi smaller lagi. Macam jadi macam ni. So this is quantum well lah. This is quantum well. So quantum dot dia akan jadi sama juga sebab we are still using the same L-gas 1.6 EV. But the material sama, cuma thickness yang kita. So bila we say quantum dot quantum well, we play with the thickness. Walaupun material dia sama. Let's see. So kita so this is the quantum dot. So and the material is 1.4 EV gallium arsenide. Tapi 1.4 EV ni band gap of a quantum dot ni dia it can vary. Dia tak semestinya sama 1.4 masa quantum well tu. Dia biasanya dia kecil sebab macam saya katakan, bila quantum dot ni dia macam jerawat yang saya kata tadi tu, become like all these bumps over here. And this bump, because it's a random process, this bump can be different sizes. So kalau besar dot tu, yang ni besar sikit ya, dot dia. So this may have a different band gap compared to this one. Okay, so tapi bila kita draw ni, kita take the average band gap. So this can remain as, kalau tulis dalam exam 1.4 pun betul, kalau buat 1.3 pun betul. So it can be slightly smaller than the band gap of the actual gallium arsenide. Cumanya, okay, perbezaan dia, so kita tengok benda sama, perbezaan dia lah yang saya cerita quantum confinement tu. Kalau bulk ni, dia punya energy state kat sini, energy state kat sini dia macam continuous lah. Ni pun continuous, ni continuous. Tapi dalam quantum well, dia punya energy state tu discrete. Bukan, discrete tu, sorry, quantum dot yang discrete. Discrete tu maksudnya dia ada satu. Energy band diagram dia tu terpisah. Discrete ni, Maksudnya energy band dia tu terpisah. Maknanya dia, kita clearly akan boleh tahu elektron duduk mana. So for example, we can make the electron to stay kat sini ke? Allah, misalnya. Dekat sini ke? Oh, dekat sini ke? Sebabnya, tapi kalau bulk, kalau kita kata elektron duduk kat sini, kita kata elektron duduk kat sini, dia boleh pergi dekat sini, kat sini, dia boleh gerak mana-mana ikut suka dia. Kalau bulk. Tapi kalau quantum dot ni, kalau dia dah duduk kat energy state ni, dia akan stay kat energy state tu. Quantum well dia discrete juga, tapi dia discrete yang dekat, yang lagi close lah, macam gini. So yang ni lagi jauh sikit dia punya gap antara setiap energy state. Yang ni lagi dekat. Tapi still confined. So mungkin dalam masa sekejap ni dengan internet yang tak bagus ni payah nak explain. So you can, this is just preliminary, you can go and read banyak video-video explaining quantum dot and quantum well, very nice videos. And these are important when you want to, soalan-soalan tentang design. So say design LED, design photodetectors, design solar cell. So, and I would normally soalan saya kata design such that is the most efficient that you optimize the design. Bila ada soalan perkataan optimize tu, awak kena fikir segala cara untuk membuatkan dia lebih efisien. So salah satu efisiennya ialah with quantum dot and quantum well. Tapi awak kena, because soalan design, you need to be able to tell me what are the material that you chose for the quantum well and quantum dot. You need to be able to draw the energy band diagram, and you need to be able to draw structurally. Kalau tak 3D macam ni pun dah okay, 2D. Okay, dia masa dah. Any question? Tak ada. Ada ke tak ada? Semua faham? Nanti mungkin ada.
Madam,
Yes.
kalau elektron tu tak bergerak, maksudnya tak ada current kan?
Good question. Dia ada current, tapi dia okay. That's a good question. So let me. Then you need to. Dia boleh lalu, tapi dia masih akan confine macam mana? That's a good question. So, macam gini. Kalau ni material kan, kalau kita apply kali lain jauh. Katalah kita apply negative over here, positive over here. So kalau kita forward bias lah. Tapi ni bukan PN junction, ni just material. Tapi kalau semiconductor material pun bukan device lah. Awak ambil seketul semicon ni, lepas tu awak letak voltage kat dia either end. Dia still akan have current flowing through. So cuma resistance dia lagi besar daripada wire. So elektron tu kata kita ada di confine kat sini kan, elektron akan lalu lagi dekat gigi macam ni. Tapi pada masa yang sama ada some akan duduk kat sini. Dia macam dia akan duduk sekejap, betul dia boleh keluar balik macam itu. So there will still be current, tapi dia akan pada satu ketika dia akan ada elektron always duduk kat sini yang untuk recombination. So sebenarnya quantum web ni bagus untuk recombination process for LED. Awak nak recombination to give out light. So akan always ada elektron yang confine kat sini untuk recombine. Tapi still elektron bila elektron can go to the positive side. So elektron still ada, dia akan flow lagi. Dia ada yang masuk betul, tapi ada juga yang confine. Macam itulah. Tak semua akan terlekat kat situ sebab energy state ni tak banyak. Hanya ada berapa layer je. Sebabnya bila habis recombine, lain akan ganti. Energy state dia macam kursi. Once ada carrier dekat kursi tu, carrier lain tak boleh duduk. So kalau dah ada carrier tu dekat sini kan, So yang elektron lain tak duduk, dia kena naik atas, kena naik atas, you know. So kalau ni dah habis, ni recombine, kosong, yang lain akan ganti, sama lah juga dengan yang atas ni. Does that answer your question?
Oh, yes.
Okay, any more question? Tak ada. So don't forget to do your assignment. If you have question, ask me before the assignment ni. Awak boleh message saya ke, nak tanya apa-apa lah yang awak tak faham tentang satu benda, atau awak baca pasal video dan tak faham. So bila tengok video kena careful juga. Kadang ada video yang betul, ada video yang tak betul. You know, kadang orang tu tak pandai tapi dia explain juga ajaran sesat. So if you don't understand anything in the internet, just you can verify with me. Alright? I think that's all for today. Let's end with a doa, please. So kita akan jumpa lepas